Hey everybody, I just wanted to spend a little time going over Brown-Lemay-Burston 16.83, and this is where we decide if ions, or things that we normally consider as ionic compounds, actually have a acidic, basic, or neutral pH. And in order to do problems like this, what we have to do is consider the conjugates of the ions that are formed in solution. So the example, or not the example, but the problem I'll go through in more detail is A, when we have ammonium bromide. In ammonium bromide, when that dissolves, is going to form ammonium ions and bromide ions. Okay. Now, in and of itself, those two ions don't necessarily look intimidating or like they would have a pH. But what we have to do is we have to look at the conjugates of those two things. So bromide here, when it is going to react with water, it's going to form HBr. Okay, HBr is strong. So because this is a strong acid, it's going to only have Br minus ions in the solution. So this does not contribute to the pH. Okay, Br minus, because it's the conjugate of something strong, will stay an ion in solution, and therefore it will not contribute to the pH. But now when we look at NH4 plus, its conjugate is NH3, and this is basic. Now this guy here is weak. Okay, so because this is weak, this is a weak base. Okay, and that makes this an acid because of conjugate acid-base concepts. Okay, so that means that NH4 plus is acidic in the solution. So we have acidic and something that does not contribute to the pH. So this compound, ammonium bromide, will be found as acidic when it's dissolved. So when we go through this list of compounds, we're going to have to look and decide if the conjugates are strong or weak acids or bases. Okay. So now let's look at iron 3 chloride, Fe, that's part B of this same problem, FeCl3. So we have Fe, 3 plus, and Cl minus. When Fe, 3 plus, reacts with water, it forms the weak base iron 3 oxide, or iron 3 hydroxide. This is a weak base, so therefore this is an acid, and that contributes to the pH. Cl, this forms HCl. This is a strong acid. So because this is a strong acid, the definition of a strong acid is that they stay as ions in solution. So this never forms. This compound never forms, so it just stays as Cl minus. So this again does not contribute to the pH of the solution. So this guy is going to be an acidic compound. Okay, so for part C, okay, we have Na2CO3, sodium carbonate. Okay, so again, we break it into its ions, Na plus and CO3 2 minus, and NaOH, that's what this forms when it is in water, and this thing is a strong base. So there's no hydroxide ion that's going to form or be present in the solution because of this sodium. So this guy does not contribute to the pH of the solution. Carbonate, when this is when we have this guy forms H2CO3, and that is a weak acid. So because this guy is a weak acid, that makes its conjugate basic and that means that we are going to form some of this to make this thing basic. So that means that this is a basic solution. So it's all about logicking. I just made a gerund. It's all about using conjugate acid base ideas in order to decide if it's about what's going on there. Okay, so the next one. Okay, so now we have KClO4. When this ionizes, we get the potassium ion and we get the hypochlorite. We get the perchlorate ion. Hypochlorite, I was going the wrong way. So we get the perchlorate ion. So this forms KOH. KOH is a strong base. So that means this guy does not contribute to the pH. This thing is fully dissolved, so you don't get any OH because of the K. The K stays as an ion, so it doesn't form any KOH, and we don't get any basic activity. Okay, the same thing happens with the perchlorate ion. We get HClO4. HClO4 is a strong acid. Okay, so again, same logic, because it's a strong acid, this doesn't contribute to any overall pH because this thing ionizes completely, and so the ClO4 just stays in the solution as ClO4 and doesn't have an opportunity to make any acid to do what acids do. So this thing is neutral because they are both conjugates of strong things. And then the last one is sodium hydrogen oxalate. Okay, so let's see here. That's NaHC2O4. So sodium and hydrogen oxalate. This is a plus, this is a minus. So again, this is going to form NaOH as its conjugate. This thing, because it's strong, this is a strong base, so this does not contribute to the overall pH of the solution. This guy, its conjugate is H2C2O4. That is a weak acid. Because it's a weak acid, this thing will contribute to the overall pH, and this ends up being a base because the conjugate of a weak acid is a base, and so that means that this guy is going to form a basic solution. Okay, so that is 16.83. I hope this helps and makes some sense. Have a great day.